Yes, wonderful. So Olivier, you start recording the meeting. So again, hello to everybody. Be welcome. The idea of this meeting is to spend some time with all of you, well, with most of people who already started to work with the Uvex instrument. And well, in few words, the idea is so far the Uvex is available. You can order it for several weeks now, but we didn't communicate a lot on this product, and now we'll do some communication to give more visibility to the instrument. And the idea is that before doing that, I wanted to share with you some discussion, some feedbacks to have a quick status after a few months of using this instrument. And also, again, I want to thank you for all your contributions. What I propose is that I'll speak a little bit, not for too long. Well, by the way, I think that the total meeting will be 1.5 hours, maybe 2 hours. It depends on your questions and your comments and the discussions we have. The idea is that I'll give you a quick status of the project, what is new with the Uvex instrument, and after that, some of you will have a short presentation. And if I'm right, there will be Sean Curry, who will have a quick presentation, quick status, especially I think on the thermal behavior of the instrument. There will be then a presentation from Jacquinot. I've not seen you. Are you around, Jean? I don't know. Yes, I can see you. Yes, wonderful. So welcome, Jean. So and Jean is a newcomer to this group, and is new with the Uvex. And then we'll have a quick talk from Gary Walker, and the last one will be Olivier Garde. Okay, so if you're all of you okay, we'll do it in this order if you're okay. And that's it. And the idea is really to have a discussion. And so you feel free to ask any question, because we are not very numerous, so we can really have a discussion. So you can interrupt me when you want. And by the way, I suggest that you switch off all the microphones, but I see this is the case, just to avoid any noise on the line. But don't hesitate to open your mic if you want to participate and to talk. Okay. Well, I will talk about the motorization module of the Uvex in a few minutes, and I will show you what is the status on that. But I want to start by saying that well, I'm not very comfortable with that, and I'm even quite frustrated. And I know that some of you are also frustrated because we don't have yet this motorization module for the Uvex. And in fact, the reason for that is that we had a very high activity within Sheliak since the beginning of the year, which is of course somewhere a very good news, but the result is that we are very, very busy to manage all the orders, the manufacturing and so on, and I was not able to find enough time to work seriously on the design of this motorization. So this is the bad side of the situation. The good one is that during the last months we took some time to think about strategic plan, and now the strategic plan is ongoing. I looked for some funding that we are receiving now, so to increase the size of the company, and we are in the process of hiring people, and at the moment, and I'm looking for 3 persons, 2 in marketing and sales, and 1 for the engineering, for the development side, technical side. And this one will be mainly to replace Philip, who worked on the Uvex project. Maybe some of you did see him a few months ago, and we decided to stop his contract. I don't know how to say that exactly. Because we didn't find the right way to work together, and in fact we were not able to be efficient enough for this development. So it is a change. It is an important change. Again, the good news is that I hope that in coming weeks, months, we will really change the structure and the size of the company, of the Shellx company, and we'll really change the situation. Okay, so well, I hope I'm quite clear with this, all of this. I don't know exactly the wording in English to explain the situation, but well, for me, this is very motivating because I think that things will change. Now, you know, it all depends on who we will find in coming weeks. And I hope it will really change the face of Sheliak and will open a new page. And well, by the way, the first priority today is clearly to work on the motorization module. And quickly, the situation today is that we have a good mechanical design, but we still have to work on the software, mainly on the software and a little bit on the electronics. So I can show you. So this is a prototype. I don't know if you can see my my camera. Can you see it? I hope so. Well, tell me. So this is a Uvex prototype, okay? And well, this is the first generation prototype. So this is not exactly the one that you have. It is an older one, but you can recognize the Uvex here. And here is the motorization module that we'll put on the side. And the idea is that we have one of the motor that can move the focus mirror, you know that. So today we use it manually, and now we'll have this belt and the way to the motor to control it. And then the idea is that I can open the box here, and when I open the box, I see that I've replaced the index and all the system to move the grating angle by this small motor. Well, I hope you can see it. You have the motor here, and you have some gears here to control very precisely the system. And the idea is that we have inside this box, well, this one is a 3D printed part, but of course the production one will be in sheet metal. And inside we'll have the second motor that will control the focus, and we'll have some electronic board like this one, sorry, to control the two motors. Okay, and it of course it embeds an Arduino. Well, maybe it will not be an Arduino at the end, but this is something like that. So we have almost everything. We just have to make the software to make everything working together. And regarding the software, we also want to take the opportunity of this project to develop a protocol that we call USIS, for Universal Spectroscopy Interface System. I don't remember exactly the name, but the idea is to have a standard protocol, communication protocol between any spectroscopic device and the software. The idea is a little bit like ASCOM or INDI under Linux. The idea is to avoid developing a new protocol each time that we have to develop software or hardware. If we can propose something that could become a standard, this would be very helpful. So we have written things on the paper. We still have to develop it for real, and it will be included in this system, and it should be included in this motorization module. And Nicolas Durand, who is the software developer for Dimetra, some of you may know him. He's working hard these days to include this uses protocol into Dimetra and to have something as much generic as possible to be able, in fact, in the future, to develop new devices for spectroscopes in a very simple way, and to avoid developing new functions in Dimetra, but having something generic. So we have a lot of things, but we still have to work on the software. And at the moment, I don't know yet how long it will take. All what I can tell you is that it will be really the first priority for the development. Another thing that I wanted to share with you is that compared to the first series that most of you have today, we have changed two, I would say, details. Maybe they are not details in the mechanical design of the instrument. First, if you can see it, so here you have the button. Well, in your version, this is not a gear, but this is a button to tune the focusing of the instrument. We have added a small ball bearing inside the system to have something smoother than in the original design. So only the new generation have that. So Jean, for instance, you are, I think you are the first one to have this version. So normally the focus should be especially smooth in your case. And the other important detail that we changed is that maybe you have seen that Ken Hudson, well, he is not here today at the meeting, but we just discussed with him a few minutes before the meeting. When he received his Uvex, he had some problems because he didn't have any image, and we spent a lot of time to understand what happened. And finally, we understood that the small holder of the mirror that is used to focus the system was out of its normal position because of probably a shock during the shipment, and then it was in a position where it was totally out of its optical nominal position. And then we worked on that, and in fact we have added a small screw below this holder, and now to prevent this to happen again. So this is something, so I said thank you to Ken to discover this problem that we have, of course we didn't see it before, but so now it is deeply solved, and I'm confident that it will not happen anymore in the future. I think that's it. Well, maybe there are some other details, but really these are details. I think this is the most important. And I think that's it, but I'm sure that you have questions. So please tell me if you have questions, or if I'm not clear of anything you want.
Hi, François, it's Sean. Question about the eventual automation. I'm not concerned about timing, but will we be able to add that to our existing Uvex devices, or will they need to go back to you, or how will that work?
No, so it's an important question. You can do it by yourself. So the idea is really that you can do it yourself. So the idea is that you'll have to remove the focus button here. So it's just simple because you just have to loosen one screw, and you'll have to remove the button, the index and the button on the top. Yep. But it is accessible you don't need to open the box. In fact, you can do that only from the outside, and we'll replace the part by the motor holder, and then so it can be added also from the outside, and then you just have, after that, you just have to plug to the motor on the electronic board inside, put the cover like that, if you can see it. So, and you'll have to, well, maybe 3-4 screws. I don't remember. There is one screw here and 2 screws here just to attach that. You just have to put the belt here. I think it is a belt. Can you, or a ring? I don't know. Well, the courroie in French. And after that, we just have to finish with a small cover here to prevent any problem here. So it's really, the idea is that we can do that from outside of the instrument.
Okay.
And you okay. And
then the second question, will Dimitra then be able to read that index value into the software?
Yes. Well, of course, yes. we just still
but
have
that's
to do
the plan. That's the plan.
Yeah, sure. Clearly, this is the plan, and again, the idea is that we're working to have something very generic inside inside Dimitra, and so this is where we are currently working on. But the idea is that we don't want to have to change Dimitra each time that we'll have to add a new device. Okay, so this is why we're working on this generic specification for the communication protocol first, and second, we also Nicolas is also working to have this. In fact, the idea is that we will declare a new device just by creating a new YAML file with all the attributes, and this will be enough for Dimitra to recognize all the parameters and to be able to add the new device. Okay, so this is really the idea. So it's a little bit more complex than just adding one fixed device, but we by doing that we make things easier for the future. Okay.
Thank you.
And of course we'll need some beta testers, and I'm sure that we'll put a lot of bugs in before having something mature and so on. But okay. Any other question?
One question. I'm using the 294 camera, which has the bigger chip, and it looks like I can cover everything from 3,500 to maybe 7,000. In that case, what's the advantage of rotating the grating? Does that do things when you use the higher gratings? I'm using the 600 grating right now.
Yes, of course. Well, if you have a big chip, well, tell me if I'm right. If you have a big chip, you can see the whole spectrum in one view in low resolution or in middle resolution. I think with the, if I'm right, with the 300 lines per millimeter grating, right? But of course, if you have a higher grating like the 600, which is the standard one, then in this case, you may have to rotate it to go from one end to the other. Okay, and by the way, also remember that if you want to go to the infrared, you probably have to add a filter, order filter to prevent any order overlapping issue. Okay. Well, by the way, well, this is a detail, but I know that on my telescope, I didn't use it yet in this configuration, but you know that inside the Uvex we can remove the slit, and behind the slit we can put a filter order. Okay, but of course it requires to remove the Uvex from the scope, remove the slit from the Uvex, put things and so on. So it's not very easy. So in my case, I've put a filter wheel in front of the Uvex, in front of the slit, and now I plan to have also I plan to use the filter wheel to change the filters or not, depending on what wavelengths I will use. Of course, if you want to do that in a remote operation, using the filter behind the slit doesn't work. Okay.
That's perfect, Francois. I was going to ask exactly that same question. Can we put a filter wheel in front rather than behind?
Wow. Now I'm able to anticipate the questions. Oh.
Francois, it's Tony. Are there any engineering diagrams to give the size of the overall chassis? Just generally.
Well, no, we can. I can. Well, this is a prototype, so we are not very. I'm not designing. Well, I can tell you that I will. Well, I'll try to prepare a. I'll try to prepare a drawing on the CAD system. Just what I can show you is that the shape of the box is the same as the Uvex itself. Okay.
Yep.
And the thickness here, if I measure it, is 35 millimeters. Okay, so from here to the Uvex chassis, I add 35 millimeter.
Okay, cool.
Okay.
Thank you.
Well, plus a few screws. By the way, I didn't tell you, but we'll have some on the top here. We'll have some buttons and LEDs. Because I know that in practical, well, here we will have the USB connector and the power supply connector. Okay, and the idea is that we'll have, I think, at least 2 buttons and 2 or 3 LEDs to make sure to be able to manipulate the instruments, even if it is not yet connected to the computer. Okay.
Okay. Manual overrides.
Yeah.
Yeah.
Yeah. Okay.
Thank you.
Any other question? 1, 2, 3. Well, anyway, we can come back on this later. Can we continue? Sean, are you ready to tell us what you did? Normally, you should be able to share your screen. Yes, we can see your screen.
And do you see the slides?
Yes, yes.
And Francois, I'm going to surprise you a little bit because I'm not going to focus on the temperature issue. I'm going to just kind of give an overview of my experience so far. And I think that might be helpful to, especially to some new users or potential users. And
perfect. And really, just I wanted to just emphasize the thing that I know that you did work hard on this temperature issue, and I think this is something very interesting to discuss. But okay,
and
go ahead.
I was thinking maybe later as a group we could talk about that a little bit too. So what I want to say up front too is that I really like working with the Uvex. It's been a lot of fun. It's been a challenge, you know, learning a new instrument and so on. And also, I want to make it clear, I'm not an expert spectroscopist at all. There are a lot of other people in this group who know a lot more than me. And working with the group has been very, very helpful. But I thought I'd take you through a little bit about what I've done and learned so far and see if it's interesting. So here's my current setup. I have a plane wave CDK 12.5. That's an f8 corrected Dahl-Kirkham telescope. And I've just put it on a new plane wave L350 direct drive mount, which I really, really like. This has been a great upgrade. And here's the Uvex sitting on the back here. And I've got the 183 camera, and I'm going to talk later about the guide camera. And this was a little supplementary weight here for those of you who worked with the plane wave mounts. You know, you have to balance them quite carefully. I've actually been able to do some shifting around and have removed this. And the back end of the Uvex now clears the base of the mount here by less than a millimeter. So it's a tight squeeze in there. So Francois, please don't extend the back of this too much further, or I'm going to have to move things around. By the way, this is also my observatory. I'm in Southern Oregon, in an interior valley, so it's usually hot and dry most of the year. So I just put a scope stuff cover over this, but I think this winter I'm going to build a roll-off roof observatory over this thing. Here's one of the little mods I did. I bought this little $15 RF controller on Amazon. It's got 2 relays in it, and it comes with a couple of little garage door opener type controllers with an A and a B button, so I can turn the calibration lamp and the flat lamp on without touching the instrument. Now, this is no Spox. It doesn't have any kind of programmability or controls, automated control. It's manual, but it means I don't have to touch the instrument. And actually, I think for about $20, I can get a 2-relay Wi-Fi enabled controller too. So maybe I'll upgrade to that in the future. And I know some of you have done work with other more capable controllers, but what I was finding was that touching the Uvex to flip the switches on the calibration unit was not a good idea. You want to be hands off, obviously. So this has, for a few dollars, has made that possible. Here's another thing I've done. Any of you who've worked with multiple gratings, and especially when you're in the 600 or higher line gratings and are shifting the grating angle, where the heck are you? It's not always easy, especially if you don't know all of the lines. So what I've done is found a position. For example, here's a 600 line grating setting that gets from H beta to H alpha. And I've taken a picture of that setting and put it in Evernote with an approximate pixel location of this 5852 line, so that if I'm changing the instrument out in the field, it's getting dark, I'm starting to panic, I pull up this and I know exactly what I'm looking at. And as long as I get that line centered, I'm good. Here's the 600 line grading to go down further into the UV. I've identified a different line here. So things like this, little things like this, make life a lot easier. I'm sure some of you have been out there in the dusk and it's getting dark, and maybe you're trying to use the sky, a solar spectrum, and you're trying to get this thing lined up. Go ahead and find your common positions that you're going to reuse, take pictures of it, screenshots, and put it somewhere where you can find them. Makes life easier. And again, you can do this with the solar spectrum as well. So what I did was took a solar spectrum and annotated the wavelengths onto it, because again, I can't remember all this stuff. I'm getting old here. My brain doesn't work that well anymore. So this is another way. When it's getting dark, you've grabbed a solar spectrum and you think, wait a minute, what is that line? What am I looking at? So annotate things and save them. It makes life a lot easier in the long run. Auto guiding. Well, anybody who's worked with this little ASI 120 camera knows what the auto guider images are like. They're tiny, right? This is actually a good one. I can see 1, 2, 3, 4, 5, 6, 7 stars here. So I probably can find out what I'm looking at. I might even be able to plate solve this, but I did a couple of things to really help. And shout out to Pete in Australia. He kind of put me on the track of this one. I upgraded to the ASI 174 guide camera, which has a much bigger chip, right? It's 13.2 diagonal. It's twice as big on the diagonal. The downside is there's severe vignetting from the little Barlow optics on the guide module. So this will be a question to Shellyak in the future. Could we get a different optical setup for a little bigger guide camera? I don't know if that's possible. But even with that vignetting, I'm seeing a lot more stars. And it's a heck of a lot easier to make sure I'm looking at the right thing. Along those lines, with that new guide camera, because remember, you're not seeing stars through the science camera, right? I was used to my nice big field of view, seeing all sorts of stars, no problem. With the plane wave pointing model software with that bigger field of view, I was able to get, I did a 48-point model. It solved 45 of them with that guide camera, even with the vignetting and the, the optics out to the edge, you're getting seagull stars and so on. But still, look at that. I got a really nice sky model. And that combined with the bigger guide camera, I'm putting the target star not in the slit, but really close to the slit every time. And that's just made life a whole lot easier. So, if you're going to be using this small guide camera stuff, do yourself a favor, make sure you get really good pointing, because otherwise sometimes it's really hard to find out what you're looking at. I think everybody knows this, but if you're looking for guide software, use PhD2, use the slit feature to outline your slit so that you can always find it, and use the sticky lock position where it'll automatically drive the target star onto the same pixel every time. Again, been very, very helpful. Okay, Dimitra. I actually now process in Dimitra and ISIS. I use both. I use Dimitra first because it's really fast and easy. And then sometimes I want to see a little more statistical stuff or a little more detail, I go into ISIS. But here's a couple of tips for Dimitra. Figure out that central wavelength, again, going back to that image earlier. And the default range is 2000 angstroms. Remember, Dimitra solves in 2 passes, right? It does a central pass first and then a wider pass. I found even narrowing the central pass a little bit helps at times, but you want to be fairly close on this central wavelength to get a good solution. And for the second pass, I think we talked about this at an earlier talk, you want to reduce that number a little bit. I found numbers like this work really well. The other thing is I've come up with a custom calibration line list for each grading. I actually went through multiple iterations, found lines that worked, didn't work, kicked out a bunch of them. This set works every time. So take the time, come up with a 300 line list and a 600 line list that works for you. And I think you'll find your calibrations work first time every time. The other thing is that look at this number here, the A1 number, that's the dispersion. That number is very, very consistent, right? It doesn't depend on the grading angle. It depends on the grading, obviously, the 300 to the 600 and so on. That's your first clue here, that A1 value, if you're getting a good calibration besides the RMSs. But look at here, I'm getting a really good RMS. The other thing is look at, especially as you're getting this tuned in, look at your wavelength mismatches here in angstroms and identify, because there may be a line. I tend to overexpose my calibration frames to get the blue end brighter. Some of the red lines don't work very well because they get, really fat and overblown. I just kick them out. The other thing is the Uvex is very linear, right? So in fact, if you can't get solved calibration lines all the way to the red or the blue, I know you're not supposed to go outside the polynomial, but with the Uvex, it actually works pretty well because of the linearity. So don't be afraid of extending your calibration a little outside. What I'd like to see, in François, maybe with this new sort of modularized interface, is an ability to not just define a Uvex, but to define a Uvex 300 at this wavelength that says, here's my dispersion factor, here's my central wavelength, and so on, so that when I start a calibration, that data is already there, and define that for a 300 at this wavelength, a 600 at this wavelength. I don't know if that's in the books or possible, but it would make life a lot easier. The other thing is, if you've used Dimitra, you realize once you run the calibration, you can look at your target calibrated. You might ask, why do you want to calibrate the calibration frame? This is why. Again, as you're getting going, look at the calibrated calibration frame, look at the lines that it solved and how they matched up. And this will give you a pretty good idea if you're matching on 1 or 2 lines that don't work very well. Again, I found once I get this set up once, it really works automatically from then on. And I know people struggle with calibration, but take the time up front, get yourself, you know, organized, analyze it, and from then on, use the same values over and over, and it'll work. Okay, how about some spectra? Have I actually done any spectroscopy? I've done about 50 spectra with the Uvex so far. I've done symbiotics, novae, and recently symbiotic novae, that great RSOPH, which you see on the right here. I'm in between smoke sessions. I managed to get 3 spectra of it. And it's a really interesting one. You can see the H alpha is just exploding. And I've seen some ones lately that said it's even more extreme. So that's been really fun. I've done BE stars. We're working on a project to do M and K flare stars, try to get spectroscopy and photometry on the flares. And I've done some education. I'm working with a group at North Medford High School locally, and we're putting together a little main sequence spectral atlas. This is just the beginning of it. This is an A star, well, this is Vega. We don't have an O star in here. We got one all the way down to an M star here. So again, the Uvex is really great for this, for teaching kids. So in conclusion, submit your spectra. This has been really valuable to me because it forces you to be organized and consistent and check your work. I especially go on, like, this is the BAA database. I download, I know David Boyd's on here, David and Woody's on here. Those two are kind of my gold standard. If they've done the star, I always check with what they've done to see how I'm doing. But submitting your spectra to the databases forces you to get a good process and be consistent. So the BAA's one, BE star, the best database. I've submitted a whole bunch to that. That's been really valuable. And this is a great team. They put out a really wonderful report every month on all the BE stars. And of course, the ARIS symbiotic, where there's been a ton of stuff with RSOPH, and recently François Tessier gave a really interesting talk on that. Then in conclusion, here's why I'm not doing spectroscopy. This is my skies. I don't know if you guys ever look at smoke maps, but green is good, yellow's not good, orange is bad, red is really bad. I'm right here over this is Oregon, this is California border. I'm right in here, and I've had nothing but this for a month now. It's really horrible. So that's no spectroscopy right now. I actually went out the other day and the cover on my telescope was covered with ash falling out of the sky. So really nasty. Anyways, that's it. And I'd be glad to answer any questions. But again, in conclusion, it's a great instrument, and I'm just having a lot of fun with it.
Great job, John. Great.
Yeah, thank you so much for this presentation. And well, there are a lot of things there. And well, just I've catched the remark about Demetra, how to improve Demetra by adding some parameters. So we'll discuss that later on. It's a very good idea. And well, thank you. Very, very, very informative and useful presentation. Thanks. Wonderful. Jean, are you okay to take the next one?
Yes, dear. I will try to share my screen.
Yes.
How do I do that?
You have, yes, in the bottom part, you have a share screen green button in the bottom line. Yes, we can see your screen. First slide with Uvex 600.
Okay, let me see. I guess I can also make it bigger. Is that okay? Yeah.
Maybe with the F5 to.
Yes,
it's in full screen. Wonderful.
Okay, so I'm a beginner. I received this very nice instrument at the end of July. It came together with the LP calibration and viewing modules. I equipped it with the two ATIC cameras, the 314 Plus and the ATIC 460 EX, which I essentially use the bin 11. This could be one of the questions, by the way. I tried the bin 22. The resolution was a little bit less, not very much, I should say, but a bit less. This, of course, as you know, requires a specific adapter. I have mounted it on the Celestron C11 HD, normally working at f10, but I also tried f7 with a focal reducer. And of course, with such an instrument, the photon vanished below 3800 angstroms, as expected. I have RC on order, but it's slow coming. But it was a good period for me to learn how to use this instrument. I'm observing from the town of Aix-en-Provence, a bit on the north edge of the town, fortunately, but nevertheless, the light pollution is huge, and I have wonderful spectrum of the street lights. But of course, with the systems in both Demetra and ISIS, you can take those out pretty well. I am 100% amateur, and but I do have some DLS-free experience. So it's early days, but here are some observations and some comments and questions, which I have to you guys who are much more experienced than I am. So I use, let me see, I can't see my screen. Can I move this? Yes, I can. Yes, so I use both ISIS and Demetra, and generally they give very close results. You see here the same data which has been processed by the two systems. I also use Visual Spectrum because I found that, which is a free software, which I found very good to understand the result, do a little physics, and to check the key lines of reference times that you choose. And also for choosing the argon neon calibration lines. I went through the process to try to choose the lines which don't seem to be too close to other lines, to have more isolated lines. I've not finished that work, and I'm not sure that the result is very good yet. But anyway, this is, for instance, the first spectra I did, and I found that it was very easy to obtain, and the calibration looked good. But more to say about that. The calibration was always done after the exposure, not moving the scopes. And indeed, the result looked good, but we'll have a closer look. I also used halogen calibration flats, and indeed I can confirm what has been explained very well by Christian Will, that the LP module for doing flats indeed loses very much the signals in the blue and in the UV. So even with my CHHD, I get much better response with halogen flats than with the LP module. I need, of course, to do a bit of installation to make this use of halogen lamp more easy to do. So I could get a bit more ambitious, and I did, like I've shown, I did a little tour of the sky, and with Wolf-Rayet lines and also P Cygni lines. I found that it was the finding the targets and auto guiding were very well performed with the LP module. I, in fact, had no trouble whatsoever to find the targets and be straight on. Now the resolution in the UV looked like what I was expecting to get, something like 1200, sometimes a bit better. And of course, the results on the lines are much sharper than what I used to get with the DRS in the near UV. So then, of course, there was the divine surprise of the nova. I must admit I should thank Sheilak for arranging to have a nova just after I received the instruments. I was not expecting such a present, so it's wonderful. Thank you very much. So I did spend I did a few spectra of this one. Here is one where I merge using again the visual spectrum. I merge a spectra taken in the blue part and a spectra taken in the red part. They merge quite well. And this was my first surprise that the calibration looked off all over, until, of course, I realized that I was seeing a very significant Doppler shift toward the red. So on this 27 and 28 of August, I estimated the shift to be minus 350 kilometer per second. I was rather excited to see that, because I didn't know this would be there until, of course, Oliver confirmed with a wonderful spectrum that indeed one was expecting such a shift. But of course, this raised to me the question of what are the error bars in the, how precise is the calibration? So I must admit, I don't know the answer, but I did a bit of work to try to estimate what sort of calibration error we can expect. The other finding was that I was expecting the resolution to increase in the red part. It did not. At best, it was 1300. And this is one of the open questions which I'd like to raise to this meeting. Instead, I was expecting that it could be around close to 1700, but it stayed around 1200. So the question is, what am I doing wrong? I will come back to that. So here are the, so I was very pleased, you see, and I enjoyed very much all the observation which I did. I will not bother you with all of them, but I will tell you a little bit of return of experience of what I did. First of all, I found that there was some substantial light leakage. And I found two places where this occurs. There is a slot here in this part of the box, and light is sneaking through this. And there is, this actually is the bad one, because it really illuminates a good half of the view. So it will interfere with the spectrum. And there was also, the top of the image, some leakage on this edge here. I don't know precisely where it is. The solution is extremely simple. You put a bit of Scotch tape, the black Scotch tape, and it removes it totally, essentially. So I can now do dark during daytime. Now, another thing which I found is that the M1 mirror moved spontaneously between two observations, and I was wondering why. This is a view of the Argon calibration lines taken when it has moved here. You see the center line is somewhere here, so it has moved down here to here. So it was a significant spontaneous move. And when I released a bit the blue button here, so the blocking button, then it went back to the correct place. So I believe that this locking button is actually slightly distorting the base where the M1 mirror is sitting. So here, this is one of the things which I discovered. So now I'm more gentle when I sort of block this blue button. So the resolution I already mentioned, this is my main problem at present. When I saw that, of course, I went back and I did careful focusing of the tuning of the M1 mirror, according to the very nice instruction which are given with the instruments. I also tried to tune the cylindrical lens, and I've given a view here. And here, to my surprise, I found that I could not find an optimum. With the cylindrical lens, it kept becoming better when I moved it from the right to the left until it reached the end. And by the way, when the instrument was delivered to me, it was in that position, totally on the left. So I went back to the position it was delivered to me. So I have a feeling that there is a problem there, and I wonder how it can be solved. There was also, of course, the theory of gradings tells you that if, in order to get the full resolution, you should illuminate all the lines of the grading. So indeed, you don't do that with an F10 because the instrument has been optimized for F8. So I tried a focal reducer to F7, but essentially it didn't change anything. So I'm still with that question. So on the calibration accuracy, first of all, I was a bit of surprised, and when I did ISIS with the lines which I had selected, and then when I was doing Demetra, first of all, the two spectra essentially fell on top of each other, so I didn't see much difference. Here, the three spectra that you see are the same, but they have a slightly different scale, so that we can separate them. But with the ISIS software, I had an RMS of 0.51. Then with Demetra, which used 19 lines, I had a much better RMS of 0.18. Then I did what François actually suggested in one of his mails, to look at what are the bad lines, remove them, and then try again. So I did that 3 times in the ISIS system until I went down to the 6 better lines. And you see, this is what it gives you. So essentially, there is hardly any difference between all these 3 spectra, which have wide different RMS between 0.18 to 0.51. There is a little bit of change. And this maximum change is roughly on H alpha, this is the H alpha line, is plus or minus 0.35 angstrom, which is, by the way, very small. It's something like half a pixel. I'm using a bin 1.1, it's half a pixel. So I would never have expected that it would have been that good. But anyway, this is another question I have to you, the experts. Is that a reasonable assumption to assume that the ultimate calibration is on that order? You see the same exercise done on our magnificent Nova here. This is again on H alpha. And of course, you see this red shift, which is very substantial. Interestingly, I did that the 4th of September, very recently, and I noticed that indeed the Doppler shift now is reduced. Is 210 kilometer per second. So I'm wondering whether the plasma blob, which has been ejected by the explosion, whether this is slowing down while it's trying to escape the gravity field, which is what one would expect, at least with the hands. Okay, so in short, it's a very nice instrument, and I was very happy to play with it. I am quite impatient to explore UV and infrared ranges, UV with the proper instrument. So I do have question for discussion, which is the resolution in the red part, the tuning range of the cylindrical lens, and also, but here Sean already answered partly to this question, which is to have, is there a set of the best argon neon line for accurate wavelength calibration? He already gave some clue on this. Of course, I agree with him. It will depend on the resolution of the grading, so on the grading you are using. So that's all what I have prepared to say. So maybe now I should remove the sharing of my screen. Yes, that's already done. Okay. Thank you.
Wow. Again, wonderful. Thank you very much, Jean. And I love you when you say that you are a beginner. This is very impressive. Well, there is a lot of questions and very interesting questions. I don't know if we spend some time now to discuss this question or if we wait until the other presentations. Well, maybe we can go to the other presentations and we keep the questions, because I wouldn't be surprised if in the other presentations we have some similar questions. Okay, so I've noted some of them, and well, on some of them I do have some elements, some answer maybe, or some help. On some other I don't have. For the blue, for instance, the resolution in the blue, that I don't have magic answer. But anyway, so do you agree? So we switch to the other presentations, and you keep really all your questions, and we'll discuss that afterward. Okay. So well, maybe there are other reactions from other people to the presentation from Jean. No.
Oui, juste une question.
Yes.
Le gratting du réseau, c'était combien? 600?
Oui, c'était.
Yes. The question was which gratting was it? And it was the standard gratting, the 600 lines per millimeter.
Ok, c'est par rapport à la résolution en fait.
Mm-hmm. Okay, so can we switch to Gary? Gary, are you around?
I'm sharing screen.
Yes. And I can see your screen. Yes, in full page. Wonderful.
Okay. Unlike Sean, I don't have anything to talk about except stability, and we didn't coordinate on this, but it's probably a good thing because he had a lot of very good tips that he covered in his presentation. So I'm going to talk about warm up and elevation stability. And one of the things that everybody should remember is that this is not just the Uvex. This is the Uvex plus a tube assembly plus a camera plus an on-axis guider plus a filter wheel plus a focuser and everything all together. So anyway, that's one thing to keep in mind. And the other thing is that I had sent out an early result a couple of weeks ago indicating that I did a warm-up test where I measured the calibration lines or a calibration line, or approximately 4,700 angstroms over temperature of about 11 degrees centigrade. And I got about 40 angstroms, which seemed, pretty high. And what I didn't realize at the time is that, this is sort of a so what? Yeah, you got 40 angstroms, but what does it mean? Because what you really care about is if you're going to calibrate, regularly, and this indicates that you probably need to if you have a big temperature change, what's the difference between the calibration line and your science spectrum? So I reran the test. Let me describe the test. This is a CDK14. For my science, since we've had such cloudy weather here, mirroring the kind of smoke and cloudy weather everywhere else in the world, it seems, the only way I could run this test was probably during the daytime. And I managed to get a fluorescent light from Harbor Freight Company, which is shown here with the orange handle on the end. And it's a nice fluorescent light, about 5 inches long, and it has a lot of lines. And so by putting that in the location you see here, I am able to create a pseudoscience source. And This lamp is run by 110 volts. It's a very nice unit, and it's only like $10, so it was not a big deal. So when I reran the test, this time I had a change of about 12 degrees centigrade, and this was a test where we warmed up. I started out in the morning, and then it warmed up about 12 degrees centigrade. And I recorded the center position of a line on the calibration spectrum, and likewise a line in what I call the science spectrum, which is that Harbor Freight light. And you see them plotted here. What I also did is I set this up in Maxim to run the camera so that there was a 10-minute wait between each exposure. So I took a cal frame, waited 10 minutes, took a science frame, waited 10 minutes, took another cal frame, and so on for a period of about 3 hours was the procedure. So what we really care about is the difference between these two lines. So this is a plot that shows that difference, and that difference is roughly 63 angstroms. It doesn't matter that it's 63. What we really care about is it always 63? And the answer is that I got between 62 and 64 angstroms when I measured the difference of this over 12 degrees centigrade. And so that was extremely stable. The other thing I should mention, I measured these lines not with a proper calibration, but by measuring their pixel position on the camera. And that's certainly good to 1 pixel, but it's not good to 1/10 of a pixel. So I haven't pushed the resolution of these results as far as they probably should be produced. But this certainly says that we're not worried under this scenario of being out of calibration by more than 1 angstrom. This was the temperature versus time. And you can see that with a warm-up curve like this, you get a big change in the beginning and then it tails off. The same thing, the opposite effect happens at night, where you get a large cooling in the first probably half hour, 45 minutes, and then it bottoms out. It kind of probably becomes fairly constant in temperature. And of course, if the temperature is totally constant, then you don't need to run a calibration, every 10 or 20 minutes. But that's not the effect that we have in the first, until from dark until midnight in most of our observatories. So the other thing I did is and all of the tests that I've talked about so far, the scope was in a fixed position. It wasn't moving, it wasn't tracking, it was just parked, actually pointing a little bit above Polaris. So it was about 50 degrees above the horizon, facing north. So I repeated this test at a pretty constant temperature. I didn't wait 10 minutes, but I just moved the scope in elevation. And I went everything from 8 degrees of elevation to 84 degrees of elevation and measured the science line and the cal line and the results that you can see here. And once again, we don't care about the absolute values here. What we care about is how well do these two track, because that's the result we would have if we were doing real science. And so the other thing that you see here is you see a little bit of hysteresis. In other words, I went from 8 degrees to 84 degrees, and I wanted to then go back to 8 degrees, and I wanted it to repeat, ideally the same. It didn't quite do that. There seems to be about 5 angstroms of hysteresis that are going on here. Also, at both 8 degrees and 84 degrees, I did repeat the test 3 times to make sure I got exactly the same answer, and I did. So the thing we care about is the difference, and here is a plot of the difference between those 2 lines. And here we see between 64 and 65 angstroms for the difference. So I was very, very pleased with this, and it shows that things are pretty stable, not too affected by gravity, as we would certainly all worry about with these image trains. This is what the image train looks like, and I've mentioned before in the spectroscopy discussion group, this H bracket that I have, and then I have a piece of aluminum to the Uvex. I'm using a right angle off-axis, on-axis guider, so I essentially have a diagonal in the system, and I turn the image train 90 degrees so that it will fit through the mount, the plane wave mount, and that's driven because I have an observatory and I have to clear the walls of the observatory, so the tube cannot be pushed forward too far or else it interferes. And because I was doing this in the daytime, I started taking darks and I was getting about 32,000 counts, which was pretty high. So I started to, I saw an email from somebody in the group about light leaks. And so I started taping up my Uvex, as you can see in this picture. And I knew that tape was only going to be so effective, and that if I wanted to really seal it, I was going to have to use aluminum tape, the kind of tape they use in high vacuum, or not high vacuum, but in heating and ventilation systems. The problem is that stuff isn't going to come off. So I put the blue tape down first to see if there was any effect, and then I covered it with the aluminum tape. And this is what my Uvex currently looks like, so that I can get nice darks in the daytime. And I was able to reduce that 32,000 count down to several thousand counts in the daytime. And you can still see a difference between if the sun is shining on the instrument, or whether the roof is closed and it's just daytime. Also in this picture, you can see the strap that goes from the Uvex to the H bracket, to stabilize the position of the Uvex. And so I think some of the good results on the elevation test have to be a result of having that bracket there. And so my conclusions are that the science and the cal lines track very, very well, probably less than an angstrom. For a 12-degree warm-up, calibration may be required every 10 minutes to limit the error to 1 angstrom with the scope stationary. Changing elevation may introduce an error of approximately an angstrom, no more than that. And the other thing which I didn't put on here is that maybe there's a suggestion that comes out of this that says we need to somehow in Demetra have a time series or a way to introduce a calibration every image or every X images, so that when we do time series like this or over temperature, that you can easily do that. Right now you can do it, but it's kind of like painful and one at a time and so forth. So if you want to put that on your software guys list, François, that would be great. So thank you.
Thank you very much. Again, a wonderful presentation and very, very interesting things. Well, there are a lot of comments, of course, but again, I think that we continue with the presentation from Olivier, and then we will start discuss. And but I've taken some points, and I know the time series for Demetra. We'll add it on the long list. Okay, so thank you, really, thank you. This is a very, very, very interesting feedback, and well, it's a kind of emotion, because you are all the measurements that you have done, all of you, are very different from what we have done on our side, and this is very, very interesting, and it is much better than you are talking about that than we do it, in fact. So thank you so much. Olivier?
Yes.
Take the mic so we can see your screen. And now it is in full page.
Okay. I just want to show you in this little presentation about some result I took with my my Uvex, and with the first prototype we have done with the Shellac instrument 1 year ago on a bigger telescope to show what some extreme spectrum we can do with Uvex. So I just present my observatory first. So I live in the southeast of France, close to the Alps, and I have a dome with a restricted telescope of 12-inch, and I put on this telescope my Uvex. The RC telescope is the great telescope to use because it is at f8, so very optimized for the Uvex. And I use it this telescope remotely from my house. So I remote control all the parts of the telescope on the calibration lamp of the Alpine module. So the Uvex is fixed on the back of the RC 12-inch. You can see on the picture all the parts of my Uvex. I have the RC 12-inch. I have a focuser after finger touch focuser. I have also I add a order filter. It's because it's more easy to change the order filter like this. Instead of open the box of the Uvex, change the filter and refix, screw all the Uvex. So it's just a little thing to have a better, to change wavelength very easily. So I have also an LP module to have a calibration lamp. On the two camera, first for the auto guiding, I use the ICI174 mini, this one, a very small camera. And for the science camera, I use ISI183 camera, the color version. So I do some test with 600 grating. And I take my first spectrum with Epsilon Ursus major. So you can see on the screen the first spectrum, the first row spectrum appear on my screen. Just to check if everything is okay. So the time exposure here, I think it's about 20 seconds. And in 20 seconds, I have about 40,000 ADU on a single exposure. And I have tuned my Uvex on the blue part, very blue part of the spectrum, UV, near UV part, to check where I can go far in the UV. So this is a spectrum radius, and I can go down to around 30,000, excuse me, 30,400 angstrom, but it's very noisy below. Another spectrum on the blue part of with the same grating. And I have tried to find the Huygens atmospheric ozone band below 360 nanometer. I found a publication that explains how this Huygens atmospheric ozone band appear at this wavelength range. So I put, you can see on the screen, the blue curve is my Uvex spectrum, and the black curve is the curve I found in a publication, and I mix the two together to see if I can see on my spectrum the Huygens bands of the atmosphere. So you can see that they are very similar to the model. So I think we can see this Huygens atmospheric ozone band. But I am not sure if deeper in the blue we can see something, because you know, the window in front of the science camera, it's not very good for UV part of the spectrum. And I think we have a better result if you can use another windows. We don't cut the UV part of the spectrum. So this is the test with the deep blue part of the spectrum. And I try also to go far as possible in the near infrared part of the spectrum. So this is the spectrum of Regulus. And you can see all the, some Paschen lines of the hydrogen line, close to 1 micron wavelength length. But I think, you know, why I take this spectrum like this, because I have a good reference is the telluric lines you can see on the left of the spectrum. And it's very easy to see on the raw spectrum. So that's why I calibrate my, my spectral range like this. But I think we can go far in IR if you move the spectrum again in the right parts. So because it's very difficult, I think from my opinion, it's difficult for the first look to see where we are with the 600 groove per millimeter rating. So I have wrote a spectral line atlas for the Uvex, and you have the web address below on the screen, and you can download it if you want. And I took several spectral lamp, sun, stars, and I identify all the line I can see on the spectrum, just to have a look of what we can get at different wavelengths. So there are, I think, where I test argon line, krypton line, mercury line, sunlight, I type A star or something like that. Even in the blue part of the spectrum, in the red part of the spectrum. I also test the 1800 groove per millimeter rating to have a better resolution. So I focus my Uvex on the H alpha line. And my first spectrum was on 28 Taurus in the Pleiad star. And here is a raw spectrum of 300 second exposure. And you see, we can see the double peak of H alpha line of these stars. And this is the radius spectrum of this star. And you can see also on the left, on the right, the telluric line, and you can see all the very short signal on the right part of the spectrum. But we have also tried the Uvex on a bigger telescope with Christian Buell and with Pierre Dubreuil on the C2PU Calais Observatory. It's located on the French Riviera, so in the very south of France. And we can use a 1 meter telescope, Cassegrain telescope, equipped with Uvex. So it's not very comfortable to use Uvex with this kind of telescope, but we can see that we can do some spectrum of very faint target. So here is Christian and me, and we put or tune the Uvex on the 1 meter telescope. On the 1 meter telescope, it's a Cassegrain telescope at FD9, so about 9 meter focal length. So it's very, very big focal length. And we use the Uvex with a 600 groove per millimeter grating on the standard slit of 23 micron. I think for this kind of telescope, it's better to have to increase the size of the slit, but we didn't want to change anything about the basic Uvex version. So we try with this Uvex like this, and we focus. We take a spectrum. Oh, sorry. We take a spectrum of quadruple gravitational lengths called Andromeda's parachute. I don't know if you know this target, but it's very, very faint target, but magnitude 15 to 17. And very big redshift about the Z, about 2.4 Z. So in this spectrum, what we can see, it's a Lyman hydrogen line we can see. At the rest, this line is close to the far UV, close to X-ray. So it's a very, very big redshift that we can see the Lyman line on the visible part of the spectrum. And we put on the slit, en fait, you see here the auto-guiding of the Uvex, and you will see the quadruple gravitational lens here. We have 3 bright parts named A, B, and C. On the D part, it's very, very faint, but it's about magnitude 17.7. It's very, very faint. So we didn't put this part in the slit. We put the 3 part A, B, and C into the UVS slit. And we took about 5 exposure of 900 seconds each. And we obtained this spectrum. And when we compare this spectrum with a professional spectrum, here we have in blue, we are our spectrum, and in black, we have a spectrum I found in a publication taken with the Keck Cosmic Wave Imager spectroscopy. So a very, very big telescope of 10 meters in diameter. So you can see, okay, the resolution is not the same, but you can see that the spectrum is very similar from our spectrum and from the Keck Cosmic Wave Imager. Just to see, to tell you that with the Uvex, we can take very, very faint target easily, in fact, because there are only 1 hour and 9 seconds. Yes, 1 hour and 16 minutes exposure. And finally, I just want to tell you some word about how to improve wavelength calibration with an Uvex. So I use another technique with a Bimer line of reference star, type A or B star. So I process the degree 2 polynomial calibration with the Balmer lines, and I take when I have this polygram of degree 2, I apply this polygram for all my spectrum taken with the same grating on the same position of the grating. I just repositioning my spectrum with reference line taken with an LP calibration module or other lamp like xenon lamp, argon lamp, neon lamp, or what you want. So we can see that after that this is very accurate calibration. And the same calibration polynomial I can use this same polynomial calibration for all my spectra taken with the same setup. So how I do for this? In this, you have in the dispersion tab, you have a box here we call Balmer. If you click on Balmer, you have all the Balmer line put on the first column here. And with the second column, you just tell to you is this for which coordinate x you have this value. So you check h beta, h gamma, h delta, and so on. And I take about 12 different Balmer line, and I apply degree 2 polynomial and press this button. And I have here, you have the polynomial equation. And here, the root mean square value of this calibration less than 0.1 angstrom. So it's very accurate. And you can see in a closer look all the number of this polynomial of degree 2. And of course, A0 is the first value of the spectrum wavelength in angstrom. A1 is the dispersion of your Uvex, the dispersion in angstrom per pixel. So in my case, the dispersion with the 600 millimeter grating and the ASI 183 camera, it's around 0.2 angstrom per pixel. And if you want to try it, it's easy. You have a tutorial of Christian Bull website. I show you the address on the bottom of the screen. And he explained all the he explained step by step how to calibrate this kind of spectrum. Okay, thank you for your attention. And if you have a question, I can answer.
Thank you so much, Olivier, for this great presentation again. And well, this is interesting because you have showed some things about the calibration that are very interesting. Well, anyway, who wants to have a quick reaction before starting in the discussion, or if you want to add something with your own experience with the Uvex for people who didn't speak yet? No?
François, I can add something to Jean's question about the resolution. And I think you were going to talk about it too. But one thing I would say is the resolution numbers coming from ISIS are, it's not clear exactly, and Olivier may know more about how they're calculated, but I believe they're set somewhere in the center of the spectrum somewhere. What I would suggest is if you really want to understand the resolution, take a good calibration frame and measure the full width half maximum. Let me just share my screen here real briefly. Here's what I did. I just took, with 600 line grading, I took a calibration frame and at various wavelengths measured the full width half maximum and computed resolution from that. And if you look at the straight line fit, the numbers are right on the published values for the Uvex. So up in the red, I am up around 1600, down to about 1300 in the blue with the 600 line grading. So Jean, if you have questions about your system, you might want to try doing that rather than relying on the ISIS resolution numbers.
Yes, thank you very much. I actually have done what you suggest. I went to Visual Spectrum and looked at the full width at half maximum of the calibration lines, and I did get the same value as was quoted by
Okay.
So I did the check that you suggest, not in a systematic way, but when I had tuned the instrument, you know, I carefully tuned the instrument to the best possible, and then I took some spectrum. I didn't need to be on the sky. I took the spectrum from the calibration lines, and I got the same values as the ISIS is giving, give or take 5%. So, but one of my questions is whether the cylindrical lens is actually well tuned. You know, I did that experiment to tune the cylindrical lens to focus it. It continually improved until I reached the full range of the adjustment. So I actually wonder whether I reached an optimum. I suspect I didn't reach an optimum, and my problem in resolution comes from that, but I'm not sure of that. François, is it possible to increase the range somehow?
I think you're muted, François.
Sorry, it's better like that. Sorry. What I was saying is that I see that well, Sean, on your side, when you do this calculation, you find something which is what is expected, and Jean, when you do it, it's not what we expect. So so this is a difference between your two instruments, and we have to go back to the details. I have no magic answer. To your question, does the cylindrical lens have an effect on the resolution? I would say no, and at least not in this range. You know that the cylindrical lens, the function of this lens is just that because we are using spherical mirrors that are out of axis, and that makes a quite high astigmatism. So it means that if you have a point at the input of the spectral, you will have a small line at the output. Well, because of optics law. And the cylindrical lens is there to compensate for this astigmatism, and then the idea is to reduce the vertical expansion. But it is really to concentrate more light. You can, if you want to, you can try to totally remove the cylindrical lens. You'll see that the spectrum, you'll have a spectrum, but it will be very wide, even for star, you know. So the function is really to concentrate as much light as possible in a single line. Okay, so you are really working on the vertical axis. So of course, you may have some effect on the horizontal axis, but not in such a range. So what you are showing is that you have almost the same resolution power at any wavelength, which is not what we expect. So, well, I don't think that the cylindrical lens can have an effect here, but we have to understand what happens. And also, I've seen that your cylindrical lens is tuned at the end also, which I don't like very much, of course. It should be closer to the middle of the range. But so maybe we have to look with more details to your instrument, Jean, and
yes. Could that come from the fact I'm using the Attic 460?
Well, maybe, but normally with the rings, because you have the right adapter ring, normally this ring makes that the chip is really exactly at the nominal position, which is the same as for the other cameras. So yes, well, for sure, this is a difference between your setup and Sean's setup. So we have to look at that. But I'm very comfortable that when we designed the rings, we made sure that we put the sensor at the same position, and this is something which is very critical in the system. But of course, we have to keep that in mind when we'll investigate that.
I have just a question to Jean. You tune your Uvex alone or on your own instrument?
I tune the Uvex on a table. Yeah.
But alone, but I think it doesn't work correctly, because when you tune your Uvex without any optical lens, you have not at f8. So you have a very open wide beam coming from the slit. So you can't adjust very good your Uvex like this. You need to have maybe a small optical lens close to f8 to adjust as best as possible your Uvex.
I tuned it on the argon neon lines.
Yes, but I think it doesn't work correctly. Yes, you can adjust, but you can't have a good focus on the line, and that's explain why I think you can't tune your cylindrical lines at the right place. I think. I'm not sure, but I think.
Okay.
Yep.
I'd like to just mention the evolution of this instrument compared with Uvex 3, which the high resolution grating is very difficult to adjust the exact center of the spectrum. So I've just added a little stop here. But the question I want to ask, which is the calibration here, when I calibrate neon with high resolution through the LP calibration and compare it with the neon light through the aperture of the telescope, the full width half maximums are different. And I just wonder whether the small diffusing screen here has to be adjusted so that the input to the slit is at f8 or f9, or the same as the telescope.
Okay, interesting.
Well, this is a good point. This is a good point. Well, of course, you know that the Uvex is sensitive to the aperture of the telescope, and yes, in fact, I agree that if you the calibration module, the LP calibration module, is made for f5 beam. And this is quite wide. This is really open compared to the nominal f8 for the Uvex. So maybe it can have some effect. You're right. And well, by the way, you did mention also the fact earlier, I think it was Jean, that you have much less light with the flat lamp from the calibration module, instead of putting some halogen lamp in front of the telescope. And what we have understood also, so this is an interesting point, but what we have discovered is that this is very probably the painting, the white painting on the small diffuser that blocks the UV part of the spectrum. So this is why, in fact, the LP calibration module flat lamp is an halogen lamp, so it has roughly the same temperature as the one that you can put in front of the telescope. But because of this paint, we may have some loss in the path. And probably if we find some other tape, or if we can add some other tape which will not have the same filtering effect, we may improve that. You know? Well, to come back on the resolution issue, Jean, I suggest that we work together to see how to work. What you mentioned, Sean, is very important. Christian Brill very often repeats that the resolution calculation in EASYS or in any software is always very fragile because it really depends on which line you are using to make this calculation, and it is really to be considered as a rough value and not an accurate one. So let's be careful with that. And if you want to really have the resolution, yes, do your own calculation by measuring the FWHN on several lines. Okay, but we are all okay with that. I think, Jean, if I'm right, you asked a question about what is the precision or the quality of the wavelength calibration.
Yeah, that's right. I was wondering whether there is, well, whether you know the ultimate accuracy that one can expect.
Well, no, I cannot give a magic number. But what I know is that, well, first, when we are talking about the RMS, we have to think that the RMS means this is the gap. This is the average of the gap between the actual line position and theoretical line position based of the dispersion law. So it's just a question of, does the actual calibration pattern match the theoretical pattern? Okay, so this is why it is so dependent on the reference list of lines that you are using, and this is why it's important that you do your own selection, or at least you check that in your calibration list you see that there is no line that are totally out of the calibration. Okay, so and I think that in fact Demetra does that in a generic request. So this is a general algorithm, and the quality really comes from the selection of the lines that you can make in your own situation. So I think that what you have shown is really perfect. It's very important to do this job to make sure that in your own instrument, in your own setup, you are sure that all the lines that you have kept or selected are relevant. Okay, and now I think that the only answer I have about the precision is you can just do the same measurements many times. I say 5, 10 times, and measure the dispersion between the several series. You know that. Well, I say that I know you know that because you are a scientist, and when you have this kind of error, either we are able to evaluate every single root cause for the general error, or we do something general, and we do several times the measurements, and we measure the discrepancy, the change between these different measurements. You see what I mean? And
I know what you mean. I was wondering whether there is a theoretical ultimate. There must be one, but
yes, there must be one, but
actually, there must be one. It cannot be.
Yes, there must be one. There must be one if we base the measurement on the pixel size and so on of the optics, on the schematic optics. But you know, it will also depend, for instance, on the temperature effect.
That's right. Well, there will be
it will depend on the mechanical effects that Gary you showed. So at the end, it is very difficult to say what is the limit. And by the way, again, if you make 100 measurements on the same star, you will have a better result and more accurate result than if you do only 3 exposure. You know, so this overall precision also depends on the process you are using, not only on the instrument. Okay, but what I'm saying is is a general statement. Of course, it's not related to the UX.
Yes, it certainly looks like that going to bin 1.1 improved the accuracy. So the theoretical value of the ultimate accuracy, let's assume that you don't have any drift, that the temperature remains constant, that the position remains constant, no deformation of the, then you have an ultimate accuracy. And actually, I was wondering what it is. It must be related to the resolution, of course, and the pixel size. It's already remarkable that you can go to a fraction of the pixel size. That's remarkable. But my question was, and I'm actually very pleased with that. But I was wondering how far you can go. How far you can go. And whether there must be a simple formula actually to
but John, you would also need to have a very specific set of calibration lines, because if you look at the neon argon alpy, they vary from bulb to bulb, right? The bulbs aren't consistent, each one is a little different, and also look at the width of those lines too. So the software is finding the center to a fraction of a pixel, but surely that varies too on your exposure time of the calibration frame. So I think I agree with François. I think there are so many variables in here that from our perspective, I'm not sure there's any theoretical minimum. What I always think is, based on my resolution, am I getting an RMS that's well within my resolution, to the point where if I'm getting 0.1 of an angstrom, that's not going to affect my result, basically.
I think that if we want to have a rough value, but this is not exactly what you are looking for, Jean, but I would say that we should be able to go to a tenth of a pixel, and we could consider this is a first order value. Because we have some oversampling of several pixels, then we can measure the center of any line at roughly a tenth of a pixel. So we could use that as the minimal.
But a pixel of what size?
Yeah, but and in this case, it depends on your pixel, of course, and it also.
I guess the pixel was 4.5.
Yeah, and also it depends of course on your sampling. So it's not only the pixel size, but also the number. In fact, the FWHN of the line. Okay. Sean, you also say that from one argon neon bulb to the other, you have some changes. This is true, but I think we have to be very careful. The argon lines are all at the same position. The neon line are all at the same position.
Right, the intensity may vary. Yeah,
exactly. But what I know is that, for instance, in some lamps we can see some hydrogen gas, and in some other we don't see them. And as far as I know, if you can see the hydrogen in some lamps, it looks like this hydrogen will evaporate with the time. So maybe in 1 year from now, you'll not have any more hydrogen in the lamp. And in fact, what may change is the density or the concentration of each gas that may draw to different levels of each line. And of course, if you have a mix between argon and neon, for instance, and it may change a little bit the position of the line that you measure. Okay, so for me, the difference may come from this kind of effect, and of course not from the position, the actual position of each line for a given gas, which is something which is very, very, very stable. Okay. I continue. You can interrupt me when you want. I've seen also that there are some questions in the chat. We'll try to cover them. I've seen, Christine, that you have several questions. But I do continue for the moment with the list of written. You talked about light leakage. And well, I've seen, for instance, Gary, that you have shown that you have put a lot of aluminum tape around the instrument. What I've seen on my side is, well, first, be careful, Jean, because I think that you have put also some tape, but you have put some black tape. Okay, and be careful, because this kind of black tape, so the electric tape, it may be transparent to the infrared. Okay, so it's much better to use aluminum tape like you did, Gary, to close any leakage. Anyway, if I see if I look at the instrument like this, if I remember, for me the two main source, but that I did consider that not, I think it is not a problem, but when I see your presentations, I'm not sure anymore, but so here we have the camera, okay, I hope that you can see so the camera is here, and so the cover is here, I hope. And in fact, the leakage comes from the two corners here and here, the two corners that are the closest from the camera. Okay, so if you have some lights coming in here and here, it illuminates quite directly the camera. But again, so I've seen these leakages by putting some LEDs just in front of the of the corner and so on. And for me, it was very, very minimal. Of course, when we use the instrument, usually it's during the night, so we don't really care. But maybe we have to put some parts inside the box to make sure to block these corners. And so please try to check if it is the case. I think so. I've seen, Gary, that you have put tape everywhere. I'm not sure it is useful, but again, I'm very interested.
I didn't put it everywhere. I put it only on the.
No. I was. This is Gary who put
Gary, okay.
some aluminum tape all around.
Okay.
But I've seen, if I remember correctly, Jean, you did show that it was more in the middle of the joint.
It was not the corner that you showed. It was not there because I tried that. I tried the corner because I thought it might come from there, but it was not there. But it came from this what you showed actually. This little
the slit here, the overlap between the two parts. Oh, okay. Okay.
Yeah, I just wanted to say that if I was using my unit at night, I wouldn't have bothered to tape it up. It was only because I was doing this during the day and we had clouds at night. So I'm not necessarily advocating taping up your Uvex at all. But if you're doing solar stuff or doing testing during the day, then maybe you need to do it. So
yeah, and mainly if you are doing darks during the day. With the sun, and so in this case, yes, you may have to be very careful. Anyway, taking darks during the day is always dangerous. So it's okay. So well, I think that we talked about the cylindrical lens. Something you mentioned, Jean, also the change between F10 and F7, saying that you try to open to F7 to look for better accuracy. I think, in fact, it is the reverse. So in the Uvex, the more the faster the beam. So if it is if the aperture is higher, then the resolution will be lower. Okay, and if you close, so you'll have a better quality at F10 than at F7. Okay, so because of the well, generally speaking, because of the astigmatism of the system.
So actually, the result was that I got more light, which was nice, but the resolution was the same seen from the ISIS. I didn't do the FW, the more careful check. The more careful check I did that.
Well, you can do the test. I know that personally I did some tests with the diaphragm in front of the system to see the difference, and you quickly see that with a fast beam with a high aperture, the lines are more fuzzy, in fact, and you can really see that very clearly.
The light should be.
And this is why we say that you can go up to f5 with the Uvex because there will be no loss by vigneting, but you will decrease the actual resolution. And this is why we consider that f8 is the best compromise to have the best efficiency, which matched with the Ritchie Chrétien telescope. Okay. So I think that we talked about the RMS and quality. Well, regarding the temperature stability, which is an important that we raised. Well, to be honest, on my side, when we did some tests, in fact, we at the beginning of the project, with the first prototypes, we have put the instrument in a fridge and see if there is a difference in the fridge and out of the fridge, and we didn't see any significant difference. Of course, we can always see something, but we did consider it was very negligible. And of course, what you have all showed is that maybe it's not, it's more than what I did expect. And it is real. And you have been, several of you have made measurements that are very useful and convincing. And what we thought, well, personally, I'm surprised by one simple point, is that you have this temperature sensitivity, but it doesn't depend on the focus. So I could expect that because of the temperature, you may have some dilatation. It works in English, I think, the size change because of the temperature change. And I could expect that you have to refocus, and then you change, by doing that, you change the geometry of the instrument, and then it may change the effect and the position of the spectrum on the CCD. And by the way, keep in mind that when you refocus, if you look at the optical schematic, if you refocus, you will move a little bit the spectrum on the chip. Okay, so this is because the movement of the focus is not exactly in the axis of the mirror. But this is not the case. As far as I know, when you have made all your measurements, it was with no refocusing. So this temperature change doesn't have any effect on the focusing. So it is something else. So it's a deformation of the instruments that is not linked to the dilatation. Well, this is a little bit surprising. And also, this is very interesting, Gary, what you showed with the position of the telescope. So the mechanical flexure due to the position of the sky. And well, by the way, it can depends on the spectroscope inside, but it can also depends on how the beam comes in. So it can also be the attachment. So it's quite a complex system. Anyway, the first conclusion, so we can work on how to improve this and find where are the root cause of this temperature sensitivity. And I'm interested to do it. I don't know how I'll do that, but I know that we can better and better understand this instrument. Anyway, what it shows is that you have to be very careful with the calibration. And as you said, you have to take some calibration frame quite often to be sure that you will not lose this precision. And in that, what you showed, Olivier, is also very important. So you have also say that, I think, Sean, is that the linearity of the instrument is very stable. So it means that we can establish the dispersion law, take some time to establish a good dispersion law with a high precision method. And after that, we just have to take one exposure to take one line and just recalibrate and move the calibration based on this line. And this is something that you can do in ISIS. So Olivier, you have showed how to use the Balmer lines, but in ISIS, you can also say that you can have an offset of the calibration, just that mentioning this line is at this wavelength and this X position. So it helps to recalibrate. And I think that we have to think about something like this in Demetra. So it works in ISIS. We don't have this function in Demetra, but I think that when I see what you are doing, I think this is important. So the idea to keep the same dispersion law is important, and not to recalibrate each time the dispersion law, to keep it for real and just adjust it using the fact that the dispersion law is very linear. Okay, so this is a point that I put in the list for Demetra.
François, tu traduiras après, mais je confirme ce qu'a dit Olivier tout à l'heure. Quand je travaille dans l'UV, les raies de Balmer, pour la calibration, c'est vraiment l'idéal, parce qu'en fait, comme tu disais, avec les contraintes pendant la nuit, il y a nécessairement le shift qui se produit avec la lampe de calibration. Mais sur les raies de Balmer, eh ben, on le rattrape, comme tu as expliqué précisément. C'est la seule solution pour s'en sortir élégamment et simplement.
So what Pierre is saying, well, Pierre is using a 3D printed Uvex, so Uvex 3, and now you're working on the Uvex 4, but the optics is the same principle. And what you are seeing is that really your experience shows that the best way is what Olivier showed, is to use the Balmer lines in ISIS, because this is very accurate, and this is a very good way to establish this dispersion law, and afterwards just move it by using one line in the calibration frame, and really it works, and then you have a very accurate system.
But François,
sorry,
yep.
I just want to add for this kind of calibration with the Balmer line, you need to don't move the grating, of course, with the same grating, but don't also move the angle of the grating, but because it's changing the dispersion law. So this method, it's good when you have a static setup. Don't move the grating, and don't change the grating, and don't move the grating angle with the same dispersion law.
Oui, avec les raies de Balmer, il est facile de refaire une calibration avec d'autres raies de Balmer. Hein. Ça, c'est pas un problème, bien sûr. Mais on ne change pas non plus lors d'une soirée le réseau continuellement non plus.
But you mean I'm not sure to understand well, of course, when you are using all the Balmer lines you have showed, when you have I think, if I remember correctly, you had 12 Balmer lines, and wow, and wow, and when you use that, you are in the blue part, of course.
Yes, of course.
Spectrum, and what you are saying is that if you establish your dispersion law with the Balmer lines, it's only valuable for the blue parts, and you cannot extend it in the red part.
You can extrapolate for the red part, but it don't work very well. So you have a bigger error in the red if you use the calibration law of the blue part. So. Okay. But you can try. In fact, when I show you my IRR in the infrared of Regulus, the infrared spectrum, I use first the law of the blue part and apply for the red part. And after, when I know where were all the passion line, I recalibrate my spectrum with all the passion line present in my spectrum.
Okay, so you use the blue dispersion law and you apply it to the red just to know where you are.
Well, yeah, just to know, because it's a
to recognize the pattern.
Yes, it's a jungle, so I just have to know where is the right Balmer line, the right passion line. Sorry.
Oui, dans le rouge et l'infrarouge, moi j'utilise les raies du néon et je fais les calibrations sur les raies de néon. Et effectivement, c'est extrêmement précis, c'est peut-être même plus précis que dans l'UV, avec les raies du néon uniquement.
Ouais, parce que tu en as plus.
Dans le rouge et l'infrarouge. Hein.
But do you use only a neon lamp, or do you use argon neon lamp?
Uniquement un néon lampe, oui, tout à fait.
Okay, okay. So what Pierre is saying is that in the red part, he's using the neon lamp, only purely neon lamp. This is interesting, with no argon. And the advantage of having a purely neon lamp is that you don't have this risk of mixing the different levels. So the accuracy of each line is higher. And of course, you know that the neon lamp has a lot of lines in the red part and almost none of them in blue part. So yes, what you are saying, in fact, is that in blue, you can use Balmer lines, and in red, you can use the neon lines and pure neon lines. Interesting. Okay.
François, I'd like to reiterate what Gary said earlier too, and it may be our use case is changing a bit. If we're just looking at one target, say 6 30-second exposures, you take calibration before and after, it's going to be fine even with some shift. But with these flare stars, for example, we may be sitting on one star for 4, 5, 6 hours. And if we're taking calibration frames all the way through, the processing then becomes complex because you essentially got to break it down into all those subsets. So long-term, the vision would be, as Gary mentioned, that some way of interspersing calibration frames, but then being able to automatically process through that entire sequence. And I realize that may be future, but it's what we're trying to do right now.
And I've written on my paper, again, this is not a promise, but I've understood that, and I've written that we should add in Demetra this time series calibration management.
Yeah.
And well, okay. And well, these are just wonderful ideas. I don't know, you know, I like to say that God did a wonderful job, but he made a big mistake with the duration of the day. Well, I think I've listed all the lines. I'm not sure, David, you did ask, you did have a remark. I'm not sure that we replied properly to your question or to your remark about the sensitivity to the tuning of your UX. Are you okay?
With the calibration?
Yes.
I think probably I need to mask the small diffusing in the Alpi calibration unit to make sure it's at F9, the same as the beam.
Yeah. Okay. Yeah.
Yeah.
I know. I think, am I right, Olivier? I think that you did it, no?
Yes. Yes. I just.
No, we cannot hear you anymore. Well, yes, I think that Olivier did it, and
in the calibration module of the Alpi calibration module, you have a white plate with coming on the main bin path, and on this plate, the white plate, you have this sticker. This sticker, I don't know if you can see it. It's a sticker with a hole, and this hole is for FD5. And what I do, it's I remove, this is the original tape inside the module, and I remove it and replace with another one with a smaller circle, a circle for FD8. So now it's work well. I have also, so the main problem is that we have not enough light as with the FD5, so I have to take more exposure to have the calibration lamp a good value of the calibration level.
And if I can add something, so it's interesting, and then David, it confirms what you are saying. But just be careful when you select your material. Make sure it's not easy that you don't have any infrared effect that is strange. You know that the soft material that we selected for making this mask is we did select it because of this infrared behavior. Okay, so it can be something, it may be surprising sometimes. Okay.
So what is the Alpi Cal module with, I don't think I have any mask on it. What F ratio is that optimized for?
It is for F5.
F5.
In the LP, the LP, generally speaking, the LP is F5 or even F4, and then we did calculate dimension this mask for F5. Roughly,
Okay.
you know, this is roughly, if you look at the flat lamp, for instance, because we illuminate by the side, in fact, you can see the shadow of the light. So it's not a perfect shape, you know, but the dimension of this mask is F5.
So if you're at F8, what's the optimum size of that hole in the mask?
Good question. I don't remember what kind of circle this is a circle of FD5, but it's smaller. For FD8, then it's smaller, but I don't remember which value I use.
Well, for me, you should take the linear dimension. If this is F5, you can do the calculation. It is divided by 5 and multiplied by 8. Or the reverse, and then you'll have the diameter. This is linear. Okay, this is a very basic geometry.
Are you going to offer that as a accessory already made?
I put it on the list.
Sorry, it's Peter here. Just to be clear, that the changing of the mask improves the flats rather than the calibration, the argon neon. Is that correct?
I think, generally speaking, it will improve everything. You know, my deep feeling is that, well, I'm not sure. So please don't change everybody this for the moment. I think this is not a very high priority. So, but if you want to push everything to the limit, this is a good point. This is a good point. But again, what is important is things like you have showed before is change it if you can make the demonstration that it will improve something. You know, please don't change things just to change things because you have heard that it's better to do that. So it's always important to decide what you are doing. Yes, David.
If I may, it's not the calibration that was the problem. It was the full width half maximum that changed when you used the calibration unit, the Alpi calibration unit, compared with a neon source through the aperture of the telescope. Not the calibration, but the full width half maximum.
Yes, but the full width at half maximum of the calibration lines.
Yeah,
and then so it's quite significant because if we said before that if you want to have an accurate measurement of your resolution, you have to measure the FWHM of your calibration lines. So of course, if by changing the mask you improve the calibration, you understand that you may improve the actual resolution of your instruments, but of course, as soon as you point at a star, you will cancel the improvement. This is something which is not real. In fact, you know what I mean? But again, this is this is something we have to permanently keep in mind, all what we are doing and where the precision comes from and so on. These are very good, very good remarks. Okay, I see that in the list we had some questions. Christine, you what about the camera choice? A small question. In acquisition with Demetra, sometime in preview mode, it doesn't work. Well, so Christine, well, I don't know if you can give more details, but maybe I don't know exactly what you are talking about. Yes, we cannot hear you for the moment. You are looking for the microphone. I see that.
Maybe it's my computer.
Oh, yes, I've got, yes, this is the fault of the computer. I love that.
I think so. Maybe I could re-download the Dimit's one.
No. Oh,
No.
no. So it will not change anything. No. Well, no. If you have some time, if the preview mode doesn't work, so please send us a screen copy and snapshot and give as much element as possible. Of course, if you say, well, sometimes it doesn't work, I know it's difficult for the developer to investigate.
Yes.
So, of course, well, but we know each other, and
Yes.
I know that. But
Yeah.
well, we have to understand what happens.
Yes, okay? It's a small detail.
Yes, but it may, well, if it prevents to observe, it's a big one. Anyway, the next question was when we will talk about camera's choice. What do you want to say about that, or do you have a question?
You told us the best camera is the AC 183.
Yep.
Yes, but is it the same thing 6 more months after?
Yeah, right now for me this is still our recommendation. So you know that the CMOS cameras, the situation is evolving, but
yes.
at the moment, this for me this is clearly the right choice for the Uvex. I know that using this CMOS camera is really a good option. It is. It has some drawbacks. Well, Olivier, I'm thinking about the problem that you have showed seen with the e-shell, which is another subject. But when you are using CMOS cameras, you have huge files, much bigger files than with the CCD camera because of the pixel size and the chip size and so on. And so there is also an important point, which is what we call the telegraph noise, and something quite complex. So we will not talk about that now. But so far the recommendation, I'm not very comfortable with that. But so far the recommendation is that it's better with a CMOS camera to record images in binning 1. Just to have some oversampling, to be able to apply some filtering to reduce the intrinsic noise of the image. But this is something which is quite complex, and in fact we usually, because the pixels are very small, we could observe with the binning 2, but using the binning 1
yes.
has the advantage of giving some margin to improve.
Yes,
to filter.
I'm sure of that. I would like to know if you have news from new cameras.
No, what I see on my side, but I've not seen any new cameras or new sensor in last few months. But
no.
What I know is that we have a new generation which is arriving, which is the ASI from
yes.
ZWO, the ASI 6200 or 6200 or the 2600. So they are the same technology, but with the
2600. 2600.
Yes.
Yes.
And
yes.
these are really the next generation with a bigger chip, with a 16-bit depth, dynamics, and with really wonderful. All is perfect in these cameras, but it is still very expensive. And by the way, they are not compliant with the Uvex because of the back focus, which is too big.
Thank you for the answer.
And well, Michel Verlinden, you didn't speak so far. You asked, and what about the sampling of the attic?
Yes, it was about. You hear me?
Yeah, I can hear you.
It was about the resolution of spectra of Jean. Yes, he used an attic 314.
Yep.
Yes, the slit 20 3 microns.
23
Yes.
or 25, yes.
So we have 3.5 pixel per per FWHM.
Yes.
I had this trouble with an LP600, the same camera, or an ATIC 414, the same pixel size, and I couldn't reach 600 as resolution, but 400 only. And I changed the camera. I took a ATIC 460, and I could reach the resolution 600. So my question is, can be the sampling a cause of the loss of resolution?
Well, you know that we have to have enough sampling in both LP600 and Uvex. You have a 1:1 ratio between the slit and the slit image on the sensor, so there is no increasing size, and then it means, yes, if you have a 23 or 25 micron slit and you have your 6.5 microns pixel with the ATIC 314, or if you have smaller pixels of 4.5 microns with the ATIC 460, if I'm right, then in any case you have enough sampling to get the resolution. So the question could be, well, can you, with the ATIC 460, can you do some binning? Well, personally, I think it would be quite limited. I would prefer to stay in binning 1:1 to make sure you keep some small oversampling. It's better than just being
some check with bin 2.2 with the ATIC 460, and indeed the resolution was a bit lower with the bin 2.2.
Yeah, because
there was some gain to be bin 1:1.
Yeah. So
that was very clear.
So, except in some case, because this is a CCD camera, when you are binning, this is a real binning, so you will increase the sensitivity. So maybe for some very faint targets, you may have the advantage to do some binning, which will not be the case with a CMOS camera. That's where very at the limit.
Yeah.
Okay. Well, do we have some other questions? Well, Peter, I know are you still there? No. Well, maybe, do you still have some remarks or any things that you want to share with the group? Are we finished? Olivier, do you think that we're missing something?
No.
Oh, we're finished? Oh.
We are talking about more than 2 hours now, so.
Okay, so maybe it's enough. Anyway, thank you very much. Thank you very much for your participation. It was very interesting to me because what you have said and showed is very interesting. All the questions are relevant. Anyway, I think that we have a great instrument in head, and we have to master it. This is a scientific instrument, so it's not a magic instrument. So we have to always take care of what we are doing with it. But well, I have a very positive feeling after this meeting, and thank you so much. And really, I can tell you that having you as a group to test and make some experiments is so efficient, is so great, and for me, really, it's a wonderful source of motivation to work together with you. And thank you. And we continue and we do our best to improve things, instruments, diameter, and so on, and hope that we will go faster and faster. And I will ask God to increase the length of the day, the duration of the day. Anyway, thank you very much.
Thanks, François, for organizing this.
Thank you very
François,
much.
very good.
Perfect.